Hello student, hi, good evening. So today we are going to see the current mirror circuit where we will find the input impedance and the output impedance of the current mirror circuit. Okay, so and also the current amplification factor in the current mirror circuit. Okay, so let's see here. This is what current mirror circuit. Current mirror circuit. Okay, so we are going to see the current mirror circuit. What is current mirror circuit? If you see, let's say this is my current source. Okay, so which is what IDC and IAC, DC current and AC current. Okay, so somewhere it is coming. Okay, so and here is this is my N-channel MOSFET, and here this N-MOS transistor. Let's say this is Q1 transistor and it is connected, and its drain and gate is connected back to back, and here is my another transistor, N-MOS transistor, and this is my drain terminal, and let's say this is my Q2 transistor. Okay, so this is my Q2 transistor, and this is also N-MOS transistor, Q1 and Q2. This is what current mirror circuit. Okay, current mirror circuit. Current mirror circuit means how much amount of current is there. Some X factor of current is there. X factor of current, ID is there. So this is my N-MOS transistor Q2 and this is transistor Q1, and here this is my drain current ID. Okay, so this is what the current mirror. Current mirror means there is a X factor of drain current. So X factor of drain current, how much X factor is this? This X factor, it depends on us, because every control is in our hand. Okay, so that is what W by L ratio. It depends on the W by L ratio. So according to that we can amplify our current here in this circuit. This is what the beauty of this current mirror circuit. Okay, so here we can amplify the current as per requirement, that is in our hand. So it is controlled by us. Okay, so by changing the W by L ratio. So now we are going to see how to find the input impedance and output impedance of this current mirror circuit. Let's see here. First, before calculating the input impedance and output impedance of this current mirror circuit, let's see here. I'm going to take one normal N-MOS circuit, okay, N-MOS transistor, and let's say this is my supply voltage VDD, and this is my N-MOS transistor, and it is source is what grounded, and this is my gate. Okay, so now see here, the small signal equivalent circuit for this N-MOS transistor is what? So let's see here, this is my gate terminal, and here is what? This is what? Gate terminal, and this gate is what? Gate is insulated with silicon dioxide. Yes, silicon dioxide dielectric. Okay, so whose dielectric constant is very high. So therefore it is like insulator, so that the impedance is approximately very large. Very large means infinite. Infinite means it is open circuited. Okay, so that's why this is what gate terminal. Gate to source connection is what? Almost open. Why? Because of silicon dioxide layer between source and gate terminal. So source and gate terminal, it is, so this is what? Open circuited because of this silicon dioxide dielectric layer. So now see here at drain side, this is my current source. Okay, so current source of what? GM VGS, and this is what? Let's say this is my output impedance, output resistance of what? R0. Yes, this is my source is grounded. So and here is gate terminal, and this is my drain terminal. This is what? Equivalent, small signal equivalent circuit for this N-MOS transistor. Based on this we are going to draw the small signal equivalent circuit for current mirror circuit. Let's see here, current mirror circuit, how to draw the small signal equivalent circuit for current mirror circuit. So that this is what my current mirror circuit is. Here, let's see, this is my current mirror circuit. This is current is what? DC current, DC plus AC current. Okay, so now this is what connected to N-MOS transistor. Okay, so this is my N-MOS transistor, and this is where the drain and gate are tied together, and this is my another N-MOS transistor, where this is my Q2 transistor and this is my Q1 transistor. Okay, so now see, so this is my drain terminal. So let's say here the current, if you see, this is what current mirror circuit. Now we are going to draw what the small signal equivalent circuit. Let's say this is my output voltage here. Okay, so and this is Q1, both transistor Q1 and Q2. For both transistor, gate to source voltage is what similar. Okay, so gate to source voltage we can see here, VGS1 is equal to VGS2 is equal to VGS. Okay, so gate to source voltage for both the transistor are equal because the gate is common for both the transistor. Now see here how to draw the small signal equivalent circuit for this. Let's say this is what grounded. Now see here, let us take this what gate. Okay, I am taking here gate. Gate is why? Because gate is common, and I am representing this voltage at what VGS positive and negative. Yes, so this is what common. This is what common for both the MOS transistor and MOS transistor. So let's say here left side, if we see left side, what is here? Current source. So let's say I am representing this current source here. Yes, because DC current will get eliminated during during small signal analysis. Only the AC current will come into the picture. So that is, I am representing it as here IAC current. Okay, so now see here, and this here the output resistance is what R01. Okay, this output resistance is because of the channel length modulation that come into the picture. So because of channel length modulation, so we are taking the channel length modulation into the account. We are taking consideration of channel length modulation. That's why this resistance is coming here. Then after that, here is what my current source. This is my current source. Let's see, this is what GM1 VGS. Okay, so this is my current source. Let me represent this common gate here so that sufficient gap must be there. So this is my gate and this is my VGS, positive, negative. And you see here, this is what open side. This one is what source. Okay, so because you know this gate to source terminal is open for both the transistor here. This is what gate to source terminal is also common for this. Yes, this is what grounded, and here this is the small signal equivalent circuit for this transistor, that is what Q1 transistor. Okay, now here the small signal equivalent circuit for transistor Q2 is what, see here, this is what current source. Similarly, like this current source is how much? Let's say the transconductance here is GM2 VGS. Now see, and this is my output resistance of what R02, output resistance of R02, and this is what grounded. You see, this is what actually the small signal equivalent circuit for this current mirror circuit using N-MOS transistor. Okay, N-MOS transistor. And let us make this somewhat bigger here. This is what source. Okay, you see, this is what current source that I have represented here, which is the AC current. Okay, and this is what resistance R01 due to channel length modulation, and this is current source here GM1 VGS. Okay, here also GM2 VGS is same because the gate is common for both the transistor. And here this is gate and this is my drain, and this is also my drain for Q1 transistor, drain for Q2 transistor. Okay, so this is what small signal equivalent circuit for this current mirror circuit. Okay, so now I am going to calculate what input impedance and output impedance. So let's see here how to calculate the input and output impedance for this. Let's see, here is what my input impedance. This is my input impedance. Okay, so here is what output impedance. What is this? Output impedance. How much input impedance we are facing while seeing from input side, and how much output impedance we will face while seeing from output side. So how to calculate that? So for this, what we will do, so let us, yes, here, sorry, so this one here is what, here the drain terminal and gate terminal both are connected to each other. Okay, so for Q1 transistor, this is what actually, this is the small signal equivalent circuit where gate and drain terminal, these are tied together. Now here we are going to find the input impedance of this current mirror circuit in small signal equivalent circuit. That is, assume that this is what my voltage Vx at node X. Okay, how much Vx is this? Now here I am going to apply how much input impedance is there. So for a time being, okay, so for a time being, what I am going to do here, I am going to remove this input AC current. Okay, so for the calculation of what input impedance, this is positive, this is negative, and let's say this is my Vx voltage, and the current here is coming what Ix. Ix current is coming. Now I am going to apply what here KCL. So for calculation of input impedance, okay, if you say by applying KVL in this loop, see here, this is Vx voltage, Vx, and this is VGS. By applying KVL at the outer loop, what we will get here, Vx minus VGS is equal to what? 0 volt. So this means what? Vx is equal to what? Vx is equal to VGS. So this is what Vx. Now again, this is what KVL. We have applied the KVL by which we get Vx is equal to VGS. Now we are going to apply KCL at node X. Now by applying KCL at node X, what we will get here? So see here, Vx divided by R01 plus current. This is going current, outgoing current, GM. So GM VGS. What is VGS? Actually VGS is also Vx that we have calculated. Yes, VGS equal to Vx, outgoing current, and here if you see there no current is flowing, so this is 0 ampere, simple 0 ampere, and here incoming current is how much? Ix is incoming current. Now here let us take the Vx common from this side. What we will get here? By taking Vx common, what we will get? 1 by R01 plus here GM1 is equal to Ix is equal to Ix. Now similarly here what we will get here? What we will get? Input impedance, input resistance as Vx upon Ix is equal to what? Rin, which is equal to here Rin, which is equal to what? 1 by R01 plus GM. This is my GM1. Okay, so this is what actually the input impedance that we are facing while seeing from input side. How much? 1 by R01 plus GM1. We can modify it also. So how we can modify it? See here, as we have obtained the input impedance is equal to what? Vx by Ix is equal to 1 by R01 plus 1 by plus what? GM. Yes, plus GM. Can I write this like this? 1 by R01 plus 1 by GM1. Yes, we can write this like this also. Yes, as we know very well that if this is what? 1 by R1 plus 1 by R2. So this is what here Rin is equal to, then we can write this as, what is this? 1 by R1 plus 1 by R2 means R1 parallel R2. This is the combination of parallel resistance, which is nothing but R01 parallel 1 by GM1. Yes, we can write like this. So this is what over input resistance that we are facing from output side. Okay, so this is what R01 parallel 1 by GM1. If you see 1 by R01, because R01 is what? Output impedance due to the channel length modulation, which is very large. Yes, as compared to 1 by GM1. So therefore we can say that this is approximately equal to what? 1 by GM1. This is approximately equal to 1 by GM1. Yes, so therefore we can say that the input impedance is what? Actual input impedance that we have obtained as Rin is equal to what? Rin is equal to R01 parallel 1 by GM1. So which is approximately equal to 1 by GM1. Why? Because if you see the R01 impedance is very large because of channel length modulation, okay, in the order of 100 kilo ohm. So that's why we are neglecting this. So we are approximating input impedance almost equal to 1 by GM1. Yes, so this is actually the input impedance of the current mirror circuit that we are facing. Okay, so in this way we can calculate the input impedance of current mirror circuit. Now see here how to calculate the output impedance of the circuit. So this is my input impedance. Okay, so please note it down first. Okay, so this is what R0 output impedance. How much output impedance we are facing here? That is what? R02 directly. Yes, if you see directly we are facing R02 output impedance, R02. Yes, which is due to the channel length modulation. How we can calculate output impedance due to channel length modulation? That is also equal to what? 1 by lambda ID. ID is what? Drain current. Yes, lambda is channel length modulation, which is in the order of 100 kilo. Yes, this is my output impedance. Output resistance and input resistance that we have obtained approximately equal to 1 by GM1 for current mirror circuit. Now this is what about the input impedance and output impedance. Now we are going to calculate what current amplification factor for this current mirror circuit. Okay, so now see current mirror circuit, how we can find the current amplification factor. For that, again let us draw again this small signal equivalent circuit, where we have eliminated the current source during the calculation of input impedance and output impedance. So that was what here, let's say this was my current, yes, AC current, which is what here IAC, this is what I, okay, IAC current, okay, I am representing it as input current I, okay, so this is what grounded, okay. So now see here, this is my output resistance of what R0, output resistance of R01, this is what R01, and this is, here is current source of GM1 VGS, okay, and here is what gate terminal, so this is positive, negative, here also this is positive, negative, and here the VGS is same. VGS is similar for both the transistors. Now here again we are going to represent as current source. This is my current source. This is what GM2 VGS, and here is my output resistance. This is what R02, and let us assume that the current is entering here. How much? I0 amount of current is entering from output side, and this is obviously, this is my what source, which is grounded. Now we are going to find what, and this is what my gate terminal, this is my drain, terminal. Now we are going to find what current amplification factor. For that, what, if you see this I0 current, this is coming from here, this is what almost short, yes, as we know very well, current always choose the short circuit path, so no current will flow through, no current is coming from here, almost zero current is coming here, and this current is equal to what, I0. So from here what we can say that I0 is how much? I0 is GM2 VGS. This is what my output current. I0 is equal to GM2 VGS. Let's say this is my equation 1. Now what we are going to see here, we want to find the input current. So let's see here, we are going to apply here KCL. Let us assume that this is what X node. Okay, so in X node this is my voltage Vx. This voltage Vx is nothing but what? VGS only. Okay, by applying KVL, so we will get this as VGS. So why? Because, sorry, here is what, again I am forgetting this one. So this is what gate and drain terminal are connected right together. So this is my VGS. Okay, VGS voltage. Now I am applying here KCL. Okay, at this node we are going to apply what? KCL. By applying KCL, what we will get? Remember this one equation, I0 equal to GM2 VGS. Okay, so now we are going to apply here KCL. By applying KCL at node X, what we will get here? This is what VGS divided by R01. Okay, R01 plus how much current is going out? GM VGS. Okay, and here plus zero current is going, and is equal to how much current is coming? I current is coming. Now take VGS common from this side. What we will get here by taking VGS common? So I am taking VGS common here. Take VGS common. So we will get here GM. This is GM1 plus 1 by R0. But 1. Okay, 1 by R01, which is equal to what? I. And this is my equation number 2. Let's say this is my equation number 2. Okay, and equation number 1, what we have obtained there? I0 is equal to what? GM what? 2. GM2 plus GM2 into VGS. Okay, GM into VGS. So here now we are going to divide this equation 1. This is my equation 1 and equation 2. Dividing equation 2 by equation 1, what we will get? We will get the current gain. Okay, so see here, this is my equation 1. I is equal to what? VGS into GM1 plus 1 by R01. I0 is equal to GM2 VGS2. We are going to divide this and we will get the current gain. How it is? Let's see. How much current gain we are getting here? So this is, let's say this is my current gain AI. AI is equal to what? I0 divided by what? I is equal to, this is what? GM2 here VGS divided by here again, this is what? GM1 plus 1 by R0 1 into VGS. Here VGS get cancelled, and we will get what? GM2 divided by GM1 plus 1 by R01. Okay, so this is GM2 by GM1 plus 1 by R0. If you see 1 by R0 is very small as compared to GM1, because R01 is very high, then the reverse is very small. So we can neglect this, and almost we are getting what? We are getting the current gain almost equal to what? So let's see here. The current gain that we get almost as AI is equal to what? AI is equal to GM almost equal to GM2 divided by GM1. Yes, GM1. So this is what? This is the current. Yes, so this is what the current gain I naught by I is equal to GM2 by GM1 is equal to Kn dash W by L to VOB divided by Kn dash W by L1 VOB. Here if you see GM2 is equal to this one. Kn dash is nothing but Kn where Kn dash is nothing but this is here nu and COX W by L. Okay, so this is my Kn dash is nu and COX. If you see this Kn dash, this is nothing but what? This is the process transconductance parameter of the MOS transistor. Okay, so and W by L is the width to length ratio. VOB is what here? Overdrive voltage, that is VGS minus VT. Okay, so now see VOB will get cancelled out, and here also process transconductance parameter Kn dash will also get cancelled out, and we are left with what? W by L2 divided by W by L1. This is the ratio. So therefore what we obtained, the current gain is equal to what? W by L2 divided by W by L1. So this is what? Current gain. Yes, current gain or current amplification in case of what? In case of current mirror circuit by using what? By using the current mirror circuit by using the MOS transistor. Okay, so by which we get the current gain as this. See, this is what the beauty of current mirror. Using what? Using the MOS transistor, where we are getting just this W by ratio. Okay, so W by L ratio, where here we want to change the current, that is in overhead. Changing current gain is in overhead. Why? Because W by L ratio that we can change. Okay, as per our requirement, we can change the W by L ratio, and in this way we can get the current gain application in case of what? In case of current mirror. Okay, so that is what all about the current mirror circuit by using the MOS transistor. We have seen what? Input impedance, output impedance, current gain amplifications for the given current mirror circuit by using MOS transistor. Okay, so that's all for today. Thank you very much.